Hey, welcome to the Explainer. So today we are pulling back the curtain on our digital world. We're going to uncover the simple, elegant rules that let our gadgets make these super complex decisions in like the blink of an eye. All right, let's jump right in. So it really all boils down to this one big question, right? How can a machine, just a bunch of simple wires and switches, actually make a logical decision? I mean, how does a chunk of silicon and metal seem to think? It really does feel like magic, doesn't it? But, it's not. It's actually one of the most brilliant ideas in all of modern engineering, and it's built on a foundation of pure, simple logic. And the answer? Well, it lies in these amazing circuits that can, for all intents and purposes, think based on a set of fixed rules. We're not talking about some super complex AI here. No, it's a very specific kind of electronic circuit designed to do one thing: process information based on these rules. And the key thing to remember is this: their output is always a direct logical consequence of whatever you put into them. No guesswork. And that brings us to the official name for this thing: a combinational circuit. Now, the best way to think about it is like a super strict referee in a football game. Seriously. This ref doesn't care what happened in the last play or who's winning or who has more fouls. They make their call based only on what they see happening at that exact moment. There's no memory of past events, no history, just a pure, logical reaction to the here and now. So what's really cool about this whole thing is that designing these circuits, it's not guesswork. Engineers don't just randomly solder wires together and hope for the best. Nope. There's a very clear, very systematic blueprint, a 5-step plan that takes you all the way from just an idea to an actual working piece of hardware. And this 5-step process, this is basically the heart of all digital design. First, you define the problem. You spell out exactly what you want the circuit to do using something called a truth table. Then, step 2, you translate that table into the language of logic, a Boolean expression. Step 3 is super important. You simplify. You make that logic as efficient as possible. Step 4, you draw the thing. You create the actual logic gate diagram. And finally, step 5, you test it. You make absolutely sure it works perfectly before you build it for real. All right, theory is great, but let's make this real. Let's take that blueprint and see how it works in practice. We're going to use it to build one of the most fundamental circuits there is. I'm talking about the circuit that lets computers do math, the adder. See, these circuits, called adders, they are the absolute foundation of all digital arithmetic. They are tucked away inside every single CPU and processor. So every time your computer calculates something in a spreadsheet or your phone renders a photo, you've got thousands, maybe millions of these little guys working together inside. So let's start with the simplest version. It's called a half adder. Its job is super, super specific. It just adds 2 single binary bits. That's it. 2 ones or zeros go in and 2 things come out: a sum and a carry. And here's its rulebook, the truth table. I mean, look, it's pretty straightforward, right? 0 plus 0 is 0. 0 plus 1 is 1. But check out that last row. What happens when you add 1 and 1? In binary, 1 plus 1 is 2, which we write as 1, 0. So the sum is 0, and we pop a 1 over to the carry output. Makes sense, right? It's just like carrying the 1 in grade school math. So that begs the question, what do you do with that carry bit? Well, that's where the full adder comes into play. It takes things one step further. It adds 2 bits, just like the half adder, but it also takes in a carry bit from a previous addition. And that one little change, that's the secret sauce. It's what lets us chain these adders together to add numbers of any size, just like how you do it on paper, column by column. Okay, so circuits can do math. Awesome. But think about your computer for a second. There is data coming from everywhere: your keyboard, your hard drive, the internet. So how in the world does a circuit choose which piece of data to pay attention to? Well, there's a great analogy for this. Imagine a DJ at a radio station. They've got multiple audio sources, maybe a record player, a laptop, a CD player. The mixing console they use to choose which one of those goes live on the air, that's doing the exact same job as our next building block. And that building block is called a multiplexer, or MUX for short. You can think of it as a data traffic controller. It's a circuit that has a bunch of input signals coming in, but it only lets one of them go through to a single output line. It's literally a data selector. But how does it choose which one to let through? That's the important part. It uses these special control wires called select lines, and these lines act like a binary address. You feed them a binary number, and that number tells the MUX exactly which input to connect to the output. Let's look at the simplest possible version, a 2-to-1 multiplexer. You've got two data inputs, let's call them D0 and D1, and you've got just one select line. If that select line is a 0, the output is whatever is on D0. If the select line is a 1, the output is whatever is on D1. It's that simple. And this is where it gets really powerful. This idea scales up beautifully. If you want to build a 4-to-1 multiplexer, you just need two select lines. 0, 0 picks the first input, 0, 1 picks the second, and so on. See that? We added just one more select line, and we doubled the number of inputs we can handle, from 2 to 4. Okay, let's zoom back out and look at the big picture. We've got these little building blocks, right? Adders that do math and multiplexers that act like traffic cops for data. They seem simple on their own, but how do these two ideas power pretty much all the technology we use every single day? Well, the truth is they're absolutely everywhere. In communication systems, a multiplexer is what lets a single fiber optic cable carry thousands of phone calls all at the same time. Inside your computer's memory, they're what let the CPU pick the exact right spot to read or write data. In your telephone network, in the arithmetic logic units of your processor, they're truly the unsung heroes of our digital world. So what are the key takeaways here? What should you remember? Well, first, that complex circuits are built using a really structured, logical process. It's not chaos. Second, simplification is key. Making the logic more efficient saves money, power, and time. And maybe the biggest one, these powerful systems are just made by combining simple building blocks, like adders and multiplexers, in really clever ways. We don't even need to see every single little gate to understand how the bigger system works. At the end of the day, every complex digital wonder we use is really just millions of simple decisions, all made in an instant. So the next time you use your phone or your computer, just remember what's really going on under the hood. It's not magic, it's just the beautiful, elegant logic of combinational circuits at work.